Hello, dear students and teachers and parents. This is Dr. Sangram Patil. I work for Sammek School, Erindol, District Jalgaon in Maharashtra. And I'm starting with chapter 1, which is Gravitation. This is Standard 10 Science and Technology book. The learning goals are to know about gravitation, Kepler's laws, acceleration due to gravitational force of the Earth, free fall, circular motion and centripetal force, Newton's universal law of gravitation, and escape velocity. There are a few questions asked in this chapter in the beginning. What are the effects of a force acting on an object? The effects of the forces on the object could be they can change the shape of the object, they can start the object moving, they can stop the moving object, or the forces can accelerate or decelerate the speed of the object. So these are the effects of the forces acting on an object. The second question, students, is what types of forces are you familiar with? And the answer to this is simple. There are four basic forces in physics. These are gravitational force, electromagnetic force, the nuclear force, which is weak nuclear force, and strong nuclear force. The third question is, what do you know about the gravitational force? This is again, you learnt it in your last last classes. The gravitational force is a force that attracts any two objects which have got masses. We call the gravitational force as attractive because it always tries to pull the masses together. It never pushes them away from each other. So every object, including us, is pulling on every other object in the entire universe. So this is a gravitational force. So let's learn something about gravitation itself. As we have learned, the phenomena of gravitation was originally described by Sir Isaac Newton, and as the story we all know, he discovered the force by observing apple falling off the tree on the ground, and then he wondered why all apples fell vertically downwards and not at an angle to the vertical, and why they do not actually fly off in a horizontal direction. Why do they always fall on the ground? So after much thinking, he came with some conclusions that Earth must have some attracting force which actually brings the apple down towards Earth itself, and this attractive force must be pointing towards the center of the Earth. The direction from an apple on the tree to the center of the Earth is vertical direction at the position of the apple, and thus the apple falls vertically downwards. Now if you look at the figure here given in your books as well, which is figure 1.1, it shows apple tree which is vertically standing on the earth. The force on an apple on the tree is towards the center of the earth, which is perpendicular from the position of the apple to the surface of the earth, and figure also shows the gravitational force between the earth and the moon. The distances, of course, they are not up to the scale. Newton thought that if the force of gravitation acted on apple on the tree at different heights from the surface of the earth, could it also act on objects at even higher distances, greater heights, much farther away from the earth, such as moon? Can it act even further like other planets or the sun? Now there's a question about Newton's laws of motion in your book. As we know from our previous standards classes, Newton described three laws of motions which are very famous in physics, and you should know them by heart. The first law is a body at rest will remain at rest, and a body in motion will remain in motion unless it is acted upon by an external force. Second law, the force acting on an object is equal to the mass of that object times its acceleration, that is F is equal to m times a. And third law is for every action there is an equal and opposite reaction. There's a little description about Isaac Newton. He was one of the greatest scientists of recent times, born in England, and he's famous for his laws of motion, equation of motion, and theory of gravity, which was described in his book Principia. Before this book actually was published, Kepler had given 3 laws describing planetary motions. However, the reason why planets move in the way described by Kepler's laws was not known. So the exact mechanism was not clear from Kepler's laws, which became more clear after Sir Isaac Newton's description of his laws of motion. Newton, with this theory of gravity, mathematically derived Kepler's laws. In addition to this, Newton did some groundwork for several areas such as light, heat, sound, and mathematics of the physics relating to the universal physics. He invented a new branch of mathematics which was called as calculus, and it has lots of uses in physics and mathematics. He was the first scientist to construct a reflecting telescope. So a lot of contribution by Sir Isaac Newton in physics, in astronomy, and in mathematics. Now let's learn about the circular motion and centripetal force. If you look at this diagram here, figure 1.2, a person has a stone tied to a string and she is moving it along the circular path. You can try it yourself. Tie a stone to one end and take the other end in your hand and rotate the string so that the stone moves along the circle as shown in the figure. But be very careful. If the stone escapes from your string, you can harm someone. So make sure there's no one around you. Are you applying any force on the stone when you do that? In which direction is this force acting? How will you stop this force from acting? And what will be the effect on the stone? So let's look into these questions. As long as we are holding the string, we are pulling the stone towards us, towards the center of the circle, and are applying a force towards it. Now the force stops acting if we release the string. In this case, the stone will fly off along the straight line which is the tangent to the circle at the position of the stone when the string is released, because that is the direction of its velocity at that instant of time. Now look at figure 1.2b, the lower one. The stone, if the string is released, it will move in the direction of the straight arrow, which is tangential to the circle, because that's the direction of the stone. But because of the string, it is being pulled towards the center and it doesn't escape until you actually release the string. You may recall that we have performed a similar activity previously in which a 5 rupee coin kept on the rotating circular disc flies off the disc along the tangent to the disc. Thus a force acts on any object moving along a circle and it is directed towards the center of the circle. This is called centripetal force. Centripetal means center seeking. The object tries to go towards the center of the circle because of the force, and in this case it is the string which keeps the stone attached to the center. Now you know that moon, which is a satellite of the earth, it goes round and round in a definite orbit around the earth. The direction of this motion of moon as well as its speed is changing constantly. Do you think some force is constantly acting on the moon? What must be the direction of this force? How would its motion have been if no such force acted on it? Do the other planets in the solar system revolve around the Sun in a similar fashion? Is similar force acting on them? What must be its direction? Now, from the above activity where you were rotating a string with the stone attached, in this example, the answers to these questions of moon and planets moving round are pretty clear. It is clear that for the moon to go around the earth, there must be a force which is exerted on the moon, and this force must be exerted by the earth, which attracts the moon towards itself. Similarly, the sun must be attracting the planets, including the earth, towards the sun because of the force, which is the centripetal force and gravitational force. Now, students, let's turn to Kepler's laws. Planetary motion was observed by astronomers in the past, and we know this since ancient times. Before Galileo, all the observations of the planets were done with naked eyes. By the 16th century, a lot of data was already available about planets' positions and their motions. Johannes Kepler studied this data. He noticed that the motion of the planet followed certain laws, and he stated 3 laws of planetary motion. These are known as Kepler's laws, and we are going to look into them in short. Now, do you know, look at this diagram now. An ellipse is the curve of 10 when a cone is cut by an inclined plane. Yeah, look at the cone cut at the inclined plane here, and whatever round shape you get is known as ellipse. Ellipse has got 2 focal points, and the sum of the distances to the 2 focal points from every point on the curve is constant. So F1 and F2 are 2 focal points of the ellipse. Look at the diagram carefully. If points A, B, and C are the 3 points on the circumference of the ellipse, then there is an equation AF1 plus AF2 is equal to BF1 plus BF2, and that is equal to CF1 plus CF2, right? So let's move on. Kepler's first law. The orbit of a planet is an ellipse with the sun at one of the foci. Now we just saw 2 foci of an ellipse, and this first law says that orbit in which the planet moves has got a shape of ellipse, and one of the foci of the orbit is the sun. Look at the diagram carefully. It shows the elliptical orbit of a planet around the sun, and the position of the sun is a red dot, which is S. That's the first law of Kepler. Second law, the line joining the planet and the sun sweeps equal areas in equal intervals of time. So AB and CD are the distances covered by the planet in equal time, that is after equal interval of time. The positions of the planet starting from A and C are shown by B and D respectively. The straight line from A to S and from C to S, these 2 lines sweep, that means they travel equal area in equal interval of time, that is the area ASB, which is area 1, and area CSD, which is area 2, are equal. Okay, so let's move on to the third Kepler's law. the square of its period of revolution around the Sun is directly proportional to the cube of the mean distance of the planet from the Sun. That's now very mathematical law, third law. So consider R as the average distance of the planet from the Sun, and T as the period, time of revolution. Then T square, R3, that is T square divided by R3 is equal to constant, which is K. So Kepler obtained these laws simply from the study of the positions of the planets obtained by regular observations. It wasn't the easy task, students. He had no explanation as to why planets obeyed these laws. We will see how these laws helped Newton in formulation of his theory of gravitation. Very interesting area. Now there's a question asked in your book. If the area ESF in figure 1.4 is equal to area ASB, what will you infer from EF? Now this explanation is similar to the above explanation. If ESF is equal to area ASB, then EF is the distance traveled in the same time as the distance traveled between A and B. Now let's look at Newton's universal law of gravitation, very important law. All the above considerations, including Kepler's laws, led Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force, and this force is proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. Let's talk a little bit about Johannes Kepler, who was a German astronomer and mathematician. He started working as a helper to another astronomer who was very famous at that time. His name was Tycho Brahe, who worked in Prague in 1600. After sudden death of Tycho Brahe in 1601, Kepler was appointed as a royal mathematician in his place. He used to observe the planetary positions made by Brahe to discover his own laws of planetary motion. And he's written lots of books. His work was later used by Newton to postulate his laws of gravity. So very interesting work done by Johann Kepler. Now, having looked at the background for Newton and Kepler, have a look at this diagram 1.5, which shows the gravitational force between two objects with masses m1 and m2. So two objects at a distance d from each other. Mathematically, the gravitational force of attraction between these two masses can be written as Fa m1 m2 divided by distance square, or F is equal to G, which is a gravitational constant, which is also known as universal gravitational constant, times m1 m2 divided by distance square. The above law means that if the mass of one object is doubled, the force between the two objects will also double. Also, if the distance is doubled, the force will reduce by a factor of 4. If the two bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. So d is the distance between the centers of the two bodies. In case when the bodies are not spherical or have irregular shape, then the direction of the force is along the line joining their centers of mass, and d is then taken to be the distance between the two centers of mass. Now from this equation, which is equation 2, we can see that the value of G is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, SI units, the value of G will equal to the gravitational force between two masses of 1 kilo kept 1 meter apart. So there's a brain teaser here. It asks us to show that in SI units, the unit of G is Newton meter square and kilogram square. The value of G was first experimentally measured by a scientist called Henry Cavendish, and the SI unit value of G is 6.673 times 10 raised to minus 11 Newton meter square and kilogram square. So they've asked you to show that the G SI unit is Newton meter square per kilogram square, which is very clear from the equation 2. The center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. The center of mass of a spherical object having uniform density is at its geometrical center. The center of mass of any object having uniform density is at its centroid. Now, why did Newton assume inverse square dependence on distance in his law of gravitation? He was helped by Kepler's third law in this, as explained below. Uniform circular motion oblique magnitude of centripetal force. Consider an object moving in a circle with constant speed. We've seen earlier that such a motion is possible only when the object is constantly acted upon by a force directed towards the center of the circle, and we've called this force as a centripetal force. If m is the mass of the object revolving and v is its speed at r radius of a circle, then we can show that this force is equal to F is equal to m times v square divided by r. If the planet is revolving around Sun in a circular orbit in uniform circular motion, then the centripetal force acting on the planet towards Sun must be F is equal to mv square upon r, where m is the mass, v is the speed, and r is its distance from the Sun, because speed is equal to distance traveled divided by time taken. The speed of the planet can be expressed in terms of the period of revolution, which is capital T, as explained below. The distance traveled by the planet in one revolution, which is known as perimeter. So perimeter of orbit is 2 pi r. We know from our mathematics the perimeter is 2 pi r, which is circumference. R is the distance of the planet from the Sun. T is the time taken for one revolution. V is the distance traveled divided by time taken. So V is equal to 2 pi r divided by T. And we know F is mv square upon r. So putting the value of V into this equation, you get F is equal to 4 m pi square r divided by t square. and now multiplying and dividing by r square in both places, we get F is equal to 4m pi square divided by r square times r3 divided by t square. And according to Kepler's third law, t square divided by r3 r raised to 3 is equal to constant. So putting this into this equation, we can say F is equal to 4m pi square divided by r square times k. Now 4 times the mass and pi square and k, these all are constant. So 4m pi square divided by k is a constant. So we can say F is equal to constant times 1 divided by r square. Students, this is a simple mathematics. So F is inversely proportional to r square. Thus Newton concluded that the peripheral force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the Sun. Newton identified this force with the force of gravity and hence postulated the inverse square law of gravitation. The gravitational force is much weaker than other forces in the nature, but it controls the universe and decides its future. This is possible because of the huge masses of planets, stars, and other constituents of the universe. Now there's a question from the book. Is there a gravitational force between two objects kept on a table or between you and your friend sitting next to you? If yes, why don't the two move towards each other? Now the answer is simple. Yes, there's a gravitational force between two objects kept apart on a table and between me and my friend, but they don't move towards each other because the intensity of the forces between two objects is very weak. So they can't move just automatically because of the gravitational force. Now students, there are a couple of examples given here and they've been solved. Mahindra and Virat are sitting at a distance of 1 meter from each other. Their masses are 75 kilo and 80 kilo respectively. What is the gravitational force between them? So we know the distance between them, which is r. We know their masses, which are m1 and m2. And we know the universal gravitational constant, which is g. And according to Newton's law, F is equal to g times m1 m2 divided by r square. And if you put everything together, F, which is gravitational force, then comes to be 4.002 times 10 raised to minus 7 newtons. That's the gravitational force between Mahindra and Virat. And though this is very small, it does exist between two objects. If the force of the friction between Mahindra and the bench on which he is sitting is 0, then probably he'll start moving towards Virat because of this gravitational force. But there is a friction, that's why he can't move towards Virat. We can calculate his acceleration and velocity by using Newton's laws of motion. Now there's a second example here, and it uses the same parameters. In the above example, assuming that the bench on which Mahindra is sitting is frictionless, starting with 0 velocity, what will be Mahindra's velocity of motion towards Virat after 1 second? And will this velocity change with time, and how will it change? So understand what we have just learned, students. The force on Mahindra we've just calculated is 4.002 times 10 raised to minus 7 Newton, and Mahindra's mass is 75 kilo. According to Newton's second law, the acceleration produced by the force on Mahindra is we know F is equal to MA. So A is equal to F divided by M. F we have just calculated. Put the figures for F, which is 4.002 times 10 raised to minus 7 divided by M, which is 75, and calculate this. So that's the answer. Now using Newton's first equation, we can calculate Mahendra's velocity after 1 second. So Newton's first equation of motion is V is equal to U plus AT. This is very important equation. Remember this. V is equal to U plus AT. As Mahendra is sitting on the bench, his initial velocity is 0. So U is equal to 0. Assuming the bench to be frictionless, put V is equal to 0 plus A. We have just calculated above. A is equal to 5.34 times 10 raised to minus 9 times T. Time is 1 second. Okay. So the answer is 5.34 times 10 raised to minus 9 meters per second. That's Mahendra's velocity at the end of 1 second. Now, this is extremely small velocity, very slow speed. The velocity will increase with time because of the acceleration. The acceleration will also not stay constant because as Mahendra moves towards Virat, the distance between them will reduce, and that will cause increase in gravitational force between them, and that will cause increase in acceleration according to Newton's second law. So I hope you understood this. Let's move on. You must know about high and low tides that occur in the sea. The level of seawater at any given location along seashore increases and decreases 2 times in a day at a regular interval. High and low tides occur at different times at different places. So in India, high tide, if it occurs at 7 o'clock in the evening, it's not same in say Afghanistan, so or in Pakistan where there is a sea. The level of water in the sea changes because of the gravitational force exerted by the moon. Water directly under the moon gets pulled towards the moon, and the level of the water there goes high, and that is a high tide. At two places on the earth at 90 degrees from the place of high tide, the level of the water goes down, and that is a low tide, which is explained in figure 1.6. So exactly close to the moon and 180 degrees away from moon, there is a high tide, and 90 degrees from these two high tide places, you have a low tide. Now let's learn a little bit about Earth's gravitational force. Will the velocity of a stone thrown vertically upwards remain constant, or will it change with time? How will it change? Why doesn't the stone move up all the time? Why does it fall down after reaching a certain height? What does its maximum height depend on? Very interesting. The Earth attracts every object near it towards itself because of the gravitational force. The center of mass of Earth is situated at its center, so the gravitational force on any object due to Earth is always directed towards the center of the Earth. Because of this force, an object falls vertically downwards on the Earth. Similarly, when we throw a stone vertically upwards, this force tries to pull it down and reduces its velocity. Due to this constant downward pull, the velocity becomes zero after a while. The pull continues to be exerted and the stone starts moving vertically downwards towards the center of the Earth under the influence of gravity. Now there are a couple of solved examples in your book. Example 1, calculate the gravitational force due to the Earth on Mahendra in earlier example. Now we know mass of the Earth, m1, 6 times 10 raised to 24 kilos. Radius of Earth, r, is equal to 6.4 10 raised to 6 meters. We know Mahendra's mass, which is 75 kilo, We know universal gravitational constant, which is G is equal to 6.67 times 10 raised to minus 11 Newton meter square per kilogram square. And using the force law, the gravitational force on Mahendra due to Earth can be calculated by this force as 1.83 times 10 raised to 9 times larger than the gravitational force between Mahendra and Virat. So it's using the same equation. F is equal to G times M1 M2 divided by R square, and putting those figures into the equation, F is equal to 733 newtons. So go through this example again. You can pause the video and go through it again. Example 2. Starting from rest, what will be Mahendra's velocity up to 1 second if he is falling down due to gravitational force of the Earth? So now here, the same equation, V is equal to U plus AT. U is 0. F is, we just calculated, F is 733 Newton. Mahendra's mass 75 kilo. Time is 1 second. And Mahendra's acceleration, A is equal to F divided by M, 733 divided by 75 meter per second square, and according to Newton's first law, V is equal to U plus AT. Mahendra's velocity after 1 second will be V is equal to U is 0 plus A is 9.77 from the above calculations, and T is 1 second. So V is equal to 9.77 meter per second. That's the calculation. Now, so small brain teaser here. According to Newton's law of gravitation, every object attracts every other object. Thus, if the Earth attracts an apple towards itself, the apple also attracts the Earth towards itself with the same force. Why then does the apple fall towards the Earth, but Earth does not move towards the apple? The gravitational force due to the Earth also acts on the Moon, because of which it revolves around the Earth. Similar situation exists for the artificial satellites orbiting the Earth. The Moon and the artificial satellites orbit the Earth. The Earth attracts them towards itself, but unlike a falling apple, they do not fall on the Earth. Why? This is because of the velocity of the Moon and the satellites along their orbits. If the velocity was not there, they would have fallen on the Earth. Now the above question, why apple falls towards Earth and Earth does not move towards the apple? The answer to this is that the Earth's acceleration because of the pull from apple is very small, because the mass of the Earth is extremely high in comparison to apple. So there is a very minimal acceleration of the Earth. So we cannot detect the movement of the Earth towards apple. It is impossible for us to detect because of very low acceleration. Now let's move on to Earth's gravitational acceleration. The Earth exerts gravitational force on objects near it. According to Newton's second law of motion, a force acting on a body results in its acceleration. Thus, the gravitational force due to the Earth on a body results in its acceleration. And this is called acceleration due to gravity, and it's denoted as small g. Acceleration is a vector. As the gravitational force on any object due to Earth is directed towards the center of the Earth, the direction of the acceleration due to gravity is also directed towards the center of the Earth, which is vertically downwards. Now, what would happen if there is no gravity? Think. Students, without the force of gravity to hold it together, the intense pressure at its core would cause the Earth to burst open in a very giant explosion. The same thing would happen to all the other stars in the universe. eventually there would be no clumped matter like stars, planets, anywhere in the universe. And if the Earth's gravity is lost, all the items held on the surface of the Earth because of the gravity will start floating away. That will include atmosphere, water, people, cars, animals. If an object were secured strongly to the Earth, it would probably remain attached to the Earth because of that strong attachment. Now look at the second question. What would happen if the value of gravitation was twice as large? Now, if the gravity were twice as strong, the bodies possessing the same mass will weigh twice as much and they will all collapse. Now look at the value of g on the surface of the Earth. We can calculate the value by using Newton's universal law of gravitation for an object of mass m situated at a distance r from the Earth's center. The law of gravitation is, as we know, F is equal to g m. Capital M is Earth's mass, small m is the mass of the object on the surface of the Earth, divided by r square. Now F is equal to mg, we know it, so we combine these two equations, which then makes it mg is equal to capital G capital M small m divided by r square. So that leaves us with g is equal to capital G capital M divided by r square, and you put all the figures into this equation, you will get small g is equal to 9.77 meter per second square. This acceleration depends only on the mass capital M and radius capital R of the Earth. So the acceleration due to gravity at a given point on the Earth's surface is same for all objects. It does not depend on the properties of the object. Now there's a question in your book. What would be the value of g on the surface of the Earth if its mass was twice as large and its radius half of what it is now? So students, we know how to calculate g. There's a formula. G is equal to capital G times capital M divided by radius, its square. Now g is acceleration because of the gravity, m is the mass of the Earth, and r is the radius of the Earth, which is distance of the object on the surface of the Earth from its center. And capital G is a universal gravitational constant, and if you make mass as twice m and radius as half the r, that is r divided by 2, then g can be calculated as small g is equal to capital G times 2 times m divided by r divided by 2 and its square. So small g will be 8 times capital G capital M divided by r square, and we know that capital G times capital M divided by r square is actual acceleration. It's a formula for acceleration of the Earth. So new g will be 8 times the actual acceleration. So new gravity would be 8 times the current value. Now let us look at some variations in value of g, small g. First is change along the surface of the Earth. Will the value of g be the same everywhere on the surface of the Earth? The answer is obviously no. The reason is that the shape of the Earth is not spherical. So the distance of a point on the surface of the Earth from its center is not same everywhere. It differs from place to place. And due to the rotation, the Earth bulges at the equator and is more flat at the poles. Its radius is largest at the equator, smallest at the poles. So the value of the G is highest at the poles because of the small distance of the poles from the center of the Earth, and it decreases from poles towards the equator gradually, and it is lowest at the equator. Second variation is change with the height. As we go above the Earth's surface, the value of radius in the equation increases and the value of G decreases. However, the decrease is rather small for heights which are small in comparison to Earth's radius. Now look at the example. Remember that the radius of the Earth is 6,400 kilometers, which is quite big. If an aeroplane is flying at a height of 10 kilometers above the surface of the Earth, its distance from the Earth's surface changes from 6,400 kilometers to 6,410 kilometers, and the change in the value of G due to it is very small, negligible. On the other hand, when we consider an artificial satellite orbiting the Earth, we have to take into account the change in the value of G due to the large change in the distance of the satellite from the center of the Earth. Some typical heights and the values of G at these heights are mentioned in this table. Have a look at these values given in this table. On the surface of the Earth, where the height is 0, G is 9.8. At the top of the Mount Everest, which is 8.8 kilometers, G is 9.8. The maximum height reached by man-made balloon is 36.6 kilometers. The value of G is 9.77. Height of a typical weather satellite, which is 400 kilometers. The value of G is 8.7 meters per second square. And height of communication satellite is 35,700 kilometers from Earth, and the value of G decreases to 0.225 meter per second square, which is quite significant drop. Now let us look at the next variation in value of G, which is change with width. The value of G also changes if we go inside the Earth. The value of radius in equation of G decreases, and one would think that the value of G should increase as per formula. However, the part of the Earth which contributes towards the gravitational force felt by the object also decreases, which means that the value of the mass capital M to be used in the equation also decreases. As a combined result of change in value of r, that is radius, and capital M, that is mass of the Earth, the value of G decreases as we go deep inside the Earth. Now let's think of these questions. Will the direction of the gravitational force change as we go inside the Earth? The answer is no. The direction of the gravitational force will not change on moving inside the Earth, because every body is pulled towards the surface of the Earth by a magnetic force. It does not change when you dig or go inside the Earth, but it will certainly change when we move from one place to another on the surface of the Earth. Now look at the next question. What will be the value of G at the center of the Earth? It will be 0. The gravitational force at the Earth's center is 0, not because there is no gravitational force down there, but because at the center we will be completely surrounded or enveloped by the Earth, and as a result will be pulled by equal forces in all directions. So the net value of Earth's gravitational force at the center of the Earth will be 0. Now every planet and satellite has different mass and radius. Hence, according to equation 6. The values of G on their surfaces are different. On the Moon, it is 1/6 of the value on the Earth's surface. As a result, using the same amount of force, we can jump 6 times higher on the Moon's surface as compared to we can do on the Earth's surface. Mass and weight. Mass is the amount of matter present in the object, and the SI unit for mass is kilograms, denoted as kg. Mass is a scalar quantity, it is not a vector. Its value is same everywhere. Its value does not change even when we go to another planet. And according to Newton's first law, it is a measure of the inertia of an object. Higher the mass, higher the inertia. Weight. Weight of an object is defined as the force with which the earth attracts the object. So it is the force on an object of mass m on the surface of the earth and can be calculated as W is equal to F, which is force, is equal to mass times gravitational force. So we know G is equal to capital G times capital M divided by R square. So weight is equal to force, so the unit is again Newton. Also, the weight being a force is a vector quantity and its direction is towards the center of the earth. Remember, mass is a scalar quantity, weight is the vector quantity. As the value of G is not same everywhere, the weight of the object changes from one place to other. Mass doesn't change, weight changes. In practical life, we use weight for both mass and weight, and the measure of weight in kilograms, which is the unit of the mass. In scientific practice, however, when we say Rajiv's weight is 75 kilo, we are talking about Rajiv's mass. What we mean is that Rajiv's weight is equal to a gravitational force on 75 kilo mass. As Rajiv's mass is 75 kilo, his weight on Earth, which is W, is equal to F is equal to M times G, and putting the values together, it is 735 newtons. The weight of 1 kilogram mass is 1 times 9.8, which is 9.8 Newton. Our weighing machines tell us the mass. The two scale balances in shops compare two masses. Now let's deal with these questions in your book. Will your weight remain constant as you go above the surface of the earth? The answer is, as you travel up from the surface of the earth, the mass will stay same, but weight will reduce as the gravitational pull on that mass will reduce as you go up and up. So as you go up away from the surface of the earth, the weight reduces, mass stays the same. Now let's look at the second question. Suppose you are standing on a tall ladder. If your distance from the center of the earth is twice the radius, what will be your weight? Again, now here the mass remains same, but the weight is going to change because you are at double the radius distance. Your weight will be 1/4 of the weight at the surface of the earth. Now your book gives this solved example. If a person weighs 750 Newton on earth, how much would be his weight on the moon, given that moon's mass is 1/81th of that of the earth and its radius is 1 3.7 of that of the Earth. Now they've given the weight on the Earth, which is 750 Newton. The ratio of the mass of Earth to mass of Moon, that is ME to MM, is 81, and the ratio of the radius of Earth to Moon is 3.7. Now mass of the person, if it is M kilo, weight on the Earth will be mg, that is 750 is equal to, we know the formula for weight is small m times capital G times capital M for Earth divided by radius of Earth, its square. So putting all the values into this, we calculate M mass as 750 times R square divided by G M. Now weight on the Moon, using the same formula as the equation 1, will be M capital G capital M Moon divided by radius of Moon its square, and then putting all the values into this equation, that gives us weight on the Moon, which is equal to 126.8 Newton. Have a look at this solved example carefully. You can pause the video or look into your book to understand if you haven't got this in first reading. The weight of the Moon on the Moon is nearly 1/6 of the weight on the Earth, and we can write the weight on the Moon as mg small m times mg small m, where gm is acceleration due to gravity of the Moon, and thus gm is 1/6 of the g on the Earth. Now a little bit about gravitational waves. Waves are created on the surface of the water when we drop stone or any object into water. Similarly, we have to have some disturbance to generate waves anywhere in the universe. Light is also a type of wave known as electromagnetic wave. Gamma rays, X-rays, ultraviolet rays, infrared rays, microwave, radio waves, these all are electromagnetic waves. Astronomical objects emit these types of waves, and we receive them using our astronomical or physics instruments. All our knowledge about the universe is based on understanding of these electromagnetic waves. Gravitational waves are very different types of waves. They have been called the waves on the fabric of space-time. Einstein had predicted their existence in 1916, and these are actually very weak and very difficult to detect. Scientists have devised very sensitive equipments to detect these waves. They come from astronomical sources. Some of the instruments are LIGO, Laser Interferometric Gravitational Wave Observatory, and similar instruments. Exactly after 100 years of their prediction by Einstein in early 20th century, scientists now have been able to detect these waves coming from different astronomical sources. Indian scientists also have contributed to the study of these waves. Free fall. Now take a small stone, hold it in hand. Which forces are acting on this stone? Now release the stone. what will happen? What are the forces acting on the stone after you release it? We know that the gravity due to Earth acts on each and every object. When we hold stone in the hand, the stone experiences gravity, but it's balanced by the force that we have applied in the opposite direction, so it doesn't drop. Now, once we release, the force from the hand is gone, and there is an unopposed gravitational force which pulls the stone down and the stone falls. Whenever an object moves under the influence of gravity alone, it is said to be falling freely. It's a free fall. The stone released from the hand just falls freely. In the free fall, the initial velocity is zero because it's in the hand. And as the stone approaches the earth, the acceleration and the velocity goes on increasing. The frictional force due to air opposes the fall. It opposes the motion of the object, and a buoyant force also acts on the object. The true free fall is possible only in the vacuum, where these forces, frictional forces due to air and buoyant force, are absent inside the vacuum. Now, for a freely falling object, the velocity on reaching the earth and the time taken for it can be calculated by using Newton's equation of motion. For free fall, the initial velocity u is 0, acceleration a is equal to gravitational acceleration g, and we can write the equation as v is equal to g times t, s is equal to half g t square, so v square is equal to twice g s. For calculating motion of an object thrown upwards, acceleration is negative, that is in the direction opposite to the velocity, and is taken to be negative g. So if we throw stone up, the gravitational force is minus g. The magnitude of g is same, but the velocity of the object decreases because of this negative g. The moon and artificial satellites are moving only under the influence of gravitational field of the earth. Thus, they are in free fall. Now, the value of g is the same for all objects at a given place on the earth. So any two objects, whatever their masses be or other properties may be, when dropped from the same height and falling freely, they will reach the earth at the same time. And Galileo is said to have performed experiment in 1590 in the city called Pisa, which is in Italy. He dropped two spheres of different masses from Leaning Tower of Pisa to demonstrate that both spheres reach the ground at the same time. When we drop a feather and a heavy stone at the same time from a height, they do not reach the earth at the same time. The feather experiences a buoyant force and a frictional force due to air, and therefore floats and reaches the ground slowly, later than the heavy stone. The buoyant and frictional forces on the stone are much less than the weight of the stone and does not affect the speed of the stone much. Recently, the scientists have performed this experiment in vacuum and showed that the feather and the stone indeed reach the earth at the same time inside the vacuum. Now let's look at these solved examples. Example 1. An iron ball of mass 3 kg is released from a height of 125 meters and falls freely to the ground. Assuming that the value of g is 10 meter per second square, calculate the time taken by the ball to reach the ground, the velocity of the ball on reaching the ground, the height of the ball at the half the time it takes to reach the ground. Now these are very important types of problems in physics, and you will need to deal with them because they'll be asked in exams, they'll be asked in your year 12 exams, they'll be there in your entrance exams. So pay good attention to this type of problems. Here m is 3 kilo, distance traveled by ball s is 125 meters, initial velocity 0, and g is equal to a is equal to 10 meter per second square. So Newton's second equation of motion, s is equal to ut plus half at square, and you put all the values together, that gives you t square as 25 and t as 5 seconds. So ball will take 5 seconds to reach the ground. And now second question is velocity of the ball on reaching the ground. So again use Newton's first equation, final velocity v is equal to u plus at, put all the values and that will give you velocity 50 meters per second, and velocity at half the time, which is t is equal to 2.5 second, and you calculate again using the same second equation, s is ut plus half at square. So s is equal to 31.25 meter, thus the height of the ball at half time will be total height 125 minus s 31.25, which is 93.75 meters. So have a look at these problems carefully. There's a similar problem here, example 2, which is a tennis ball is thrown up and reaches a height of 4.05 meter before starting to come down. What was its initial velocity? How much total time will it take to come down? Now g here again is 10 meter per second square. So for upward motion of the ball, the final velocity v is 0. Okay, so this is the difference. In the previous example u was 0, here v is 0, and distance traveled by the ball is 4.05 meters. Acceleration, because the ball is going against gravity, so the g is minus 10. So here we put a negative sign. Again use the Newton's third equation, v square is equal to u square plus 2as, and you put the values there and you will get u as 9 meter per second as the initial velocity of the ball when it was thrown upwards. Now let us consider the downward motion of the ball. The ball takes t seconds to come down. The initial velocity is 0 because it's starting from 0 when it reaches up. U is equal to 0, yeah, when it starts falling down. The distance traveled will be same, 4.05 meters, and as the velocity and acceleration are in the same direction, now g is equal to a is equal to plus 10 meter per second. So put it in Newton's second equation, s is equal to ut plus half at square, and you will get value of t square as 0.81. So that is t is equal to 0.9 second. So ball will take 0.9 second to reach the ground from the top. It will take the same time to go up. Thus the total time taken will be 2 times 0.9 is 1.8 second. Let's have a look at the concept of gravitational potential energy. Now, we've studied potential energy last year. The energy stored in an object because of its position or the state is called potential energy. And this energy is relative, increases as we go to greater height from the surface of the earth. We had assumed that time that potential energy of an object of mass m at the height h from the ground is mgh, and on the ground it's 0. When h is small compared to radius r of the earth, we can assume G to be constant and can use the formula mgh. But for large value of h, the value of G will reduce. So as the h increases, G goes down. For an object at infinite distance from the Earth, the value of G will be obviously 0, and Earth's gravitational force will not act on that object. So it's more appropriate to assume the value of potential energy to be 0 there at infinite height from the Earth. Thus, for a smaller distances, heights, the potential energy is less than 0. It is negative. When an object is at a height h from the surface of the Earth, the potential energy can be given by this equation: capital G times capital M times small m divided by r plus h. So m and r are Earth's mass and radius respectively. Now let's look at escape velocity. Now when the ball is thrown upwards, its velocity reduces because of the gravitation of the Earth. The velocity becomes 0 when it reaches the maximum height, and then it starts falling down. The maximum height depends on the initial velocity, and according to Newton's third equation, v square is equal to u square plus twice as. So v here will be final velocity, that is 0. A is gravitational acceleration because the ball will be going up against the gravity. The A is minus g. So 0 is equal to u square plus 2 times minus g times s. So the maximum height of the ball will be can be calculated as s is equal to minus u square divided by twice g. Thus, higher the initial velocity u, the larger the height reached by the ball. The reason for this is that higher the initial velocity, the ball will go against the gravity for a longer distance, and then it will achieve more height. We have seen that the value of G goes down as we go higher and higher from the surface of the Earth. The force pulling the ball downwards will go on decreasing as the ball goes up. And if we keep increasing the initial velocity, it will reach higher and higher heights. And above a particular value of initial velocity of the ball will be able to overcome the downward pull by the Earth, and the ball can actually escape the Earth forever, and it will not fall on the surface of the Earth. This initial velocity at which the ball will escape out of Earth is called as escape velocity, and we can actually calculate this initial velocity using various equations. An object going vertically upwards from Earth's surface with initial velocity equal to escape velocity, it escapes the gravitational force of the Earth. The force of the gravity being inversely proportional to the square of the distance becomes 0 only at infinite distance from the Earth. This means that for the object to be free from gravity of the Earth, it has to reach infinite distance from the Earth. The object will come to rest at infinite distance, and it will stay there. It will not come back to Earth. For an object of mass m on the surface of the Earth, we can calculate kinetic energy is equal to 1/2 mv square. Potential energy is equal to negative capital G capital M small m, which is the mass of the object, divided by r. So total energy is equal to kinetic energy plus potential energy, which is equal to 1/2 mv square minus g mm divided by R. So this is the equation for total energy on the surface of the Earth. Whereas at infinite distance from the Earth, when the object has escaped out from the Earth, kinetic energy, because it has come to still position, its kinetic energy is zero. Potential energy, if you look at the equation of potential energy, which is capital G capital M times small m divided by R. R is the distance, and because R is infinite, anything divided by infinite doesn't exist. It's almost equal to zero. So potential energy is zero. So total energy at infinite distance from Earth is equal to 0 plus 0 is equal to 0. So from the principles of conservation of energy, E1 is equal to E2. So energy remains constant. Half mv square minus gmm divided by r is equal to 0. So we can calculate velocity by rearranging this equation as v escape is equal to square root of 2 times gm divided by r, and again rearranging the stuff and putting the values together, you get the value as 11.2 kilometers per second as the escape velocity. The spacecrafts which are sent to the moon or other planets have to have their initial velocity more than escape velocity, so they can overcome Earth's gravitational attraction and they can travel to these objects. Let's look at this solved example. Calculate the escape velocity on the surface of the moon given the mass and radius of the moon to be 7.34 times 10 raised to 22 kilo and 1.74 times 10 raised to 6 meters. That's the radius. So here G, capital G, is 6.67 times 10 raised to minus 11 Newton meter square per kilogram square. We know it from our previous calculations. Mass m given is 7.34 times 10 raised to 22 kilo and radius is 1.74. So putting this into escape velocity equation, which we just saw in the previous slide, v escape is equal to square root of 2 times capital G capital M divided by r. Putting these values together, it comes to be 2.37 kilometer per second. So escape velocity from the surface of the moon is 2.37 kilometers per second. And students, finally, weightlessness in space. So space travelers and the objects in the spacecraft, they appear to be floating. You might have seen them in the videos or in movies. The space travelers, the astronauts, they float in the spacecraft. And why does that happen? Though the spacecraft is at a height from the surface of the Earth, the value of the G is not actually zero. And in the space station, the value of the G is only 11% less than the Earth's surface. The height of the spacecraft is not the reason for their weightlessness. Their weightlessness is caused by their being in the state of free fall. Though the spacecraft is not falling on the surface of the Earth, its velocity along the orbit is high. That's why it doesn't let it fall on the surface of the Earth. The only force acting on it is the gravitational force of the Earth, and therefore it is in free fall. As the velocity of free fall does not depend on the properties of an object, the velocity of free fall is same for the spacecraft, the traveler, and the objects in the craft. Thus, if the traveler releases an object from her hand, it will remain stationary with respect to her and will appear to be weightless. It's the interesting fact. Now, students, there are few exercises given at the end of your chapter. I will encourage you to go through them and solve them. They come with the answers, so you can solve them with the help of your teachers. I hope you enjoyed this chapter. For more such chapters, go to my YouTube channel, which is Dr. Sangram G. Patil, and you will get a lot of material for 10th class, which will be useful for you. So, best of luck. Take care. Bye bye.